Here is a brief introduction focused just on the WISE mission. So we'll cover, what is WISE, all the different pieces of it, what its orbit is, and why that matters. The next talk in the series will be specifically about getting WISE data out of the archive. If you want to learn more, there's two different websites that you can go to. The first one here is NEOWISE. As we'll learn in a bit, WISE was hibernated and woken up, and the woken up version is NEOWISE, and that website is there. The other website is for the original WISE mission. If you just Google WISE and Berkeley, there's another WISE project elsewhere at Berkeley that's not the same as this one. So just as an overview, WISE is the Wide Field Infrared Survey Explorer. It is a NASA-funded mission, and it is Explorer class, which in NASA speak means small budget, small spacecraft, small rocket. That's the idea. It's a 40-centimeter telescope, which is not very big, and it had with it a solid hydrogen cryostat to help keep the telescope cold. As we covered before, when you observe in the infrared, it's really helpful if your telescope is cold. And so the solid hydrogen that they carried on board helped keep the telescope cold. Originally, it covered 3.4 to 22 microns using just one instrument. It had 4 channels, 3.4, 4.6, 12, and 22 microns, otherwise known as WISE 1, 2, 3, and 4. And it observed essentially in all 4 bands at once. It was launched from Vandenberg Base here in California in December 2009. It ran out of that solid hydrogen cryogen in October 2010, which is only about 10 months after it launched. While the spacecraft continued to warm up, it did a little bit more just in 3 bands, and it did a little bit more in 2 bands, and then it went into hibernation in February 2011. We woke it up in September 2013 and restarted observing in just the shortest 2 bands in December 2013. So a critical point here is that when the cryogen was depleted, the spacecraft warmed up. And so we lost the 22 micron capability first and then the 12 micron capability. And the clever engineering that went into the spacecraft means that just passive cooling keeps the telescope cold enough for the shortest 2 wavelengths to still operate. So 2 key points. It is a survey mission. It looks at the whole sky every 6 months. Other telescopes, space telescopes such as Hubble, Spitzer, and Herschel are all pointed observatories. They only look at specific regions of the sky. WISE is in a sun-synchronous polar orbit. So it goes around the Earth at the sunrise-sunset terminator. So here's another view of this. So on a single orbit, it takes a series of slightly overlapped exposures north and south in the ecliptic plane. So it's going up or down and takes a series of pictures offset by just a little bit. And the next orbit is just a tiny bit offset. And so it covers this almost the same patch of sky, but not quite. And so after many orbits, you've covered the whole sky. So here is a video that is supposed to represent the coverage of WISE over the sky over 6 months. So the little tiny blue dot that you can't see anymore at the center of this is meant to be representational of the Earth. And the spacecraft orbits at the sunrise-sunset terminator. And so in other words, the sun is always partially risen for it. And it observes the whole sky that it can see continuously over all of its orbits. So you can see it takes a lot of exposures at the north and south ecliptic pole because it hits them every single orbit. And stuff on the ecliptic plane does not get covered as much. So the least number of frames go into things in the ecliptic plane, the plane of the solar system, and the most frames can be found at the north and south ecliptic poles above and below the solar system. The other thing to know about this orbit is that it's relatively close to the Earth. It orbits every 90 minutes or so. And so you do have to worry about the radiation belts, the Van Allen radiation belts around the Earth. The spacecraft has to be careful when it's going through the radiation belts. And it has to worry about not looking at the moon, because the moon is very bright and it would heat up the spacecraft perceptibly. So you have to you have a little bit of flexibility in exactly where you're pointing. And so they have a little bit of flexibility in order to try to look away from the moon and not worry so much about the radiation belts. So the survey started in 2010, and this is in the galactic coordinates. You can see it's mapping out the whole sky in 6 months. So you can see there's some stripes they do more frequently. That's because they're stepping around the moon, but you can see it covers the whole sky. So this is what the WISE spacecraft looks like. There's the light comes in from the top, and you had the cryostats. The solid hydrogen was sort of in a ring around it, and then the mirror is down there, and the instruments are down there. So this is WISE being assembled. It just really, I just wanted to show you this to just demonstrate it is really not a big spacecraft. The mirror diameter is only 40 centimeters. It is very small, even compared to Spitzer and Herschel is enormous with a 3.5 meter mirror. Spitzer has an 85 centimeter mirror. WISE is less than half the size of Spitzer. These are more pictures of it going into its rocket. You can see it's so small it almost looks lonely inside the rocket fairing there. That's half the rocket fairing on, and this is about when they're about to put the other half of the rocket fairing on. So a brief timeline of WISE. This is going to be important for understanding ultimately which data releases are which. So it was launched in December 2009. It finally cooled off enough that they could start their survey in January 2010. They completed their first pass of the sky 6 months later in July. And the spacecraft was still at 12 Kelvin. But by August, they were starting to warm up. It was the end of the 4-band cryo observations and the start of just the 3-band cryo. Eventually, the cryo runs out too. So by the end of September, there was not even 12 microns anymore, and it was the start of 2-band only. So the temperature was rising to 45 and then 75 Kelvin during this process. So in February 2011, there wasn't any money to keep running WISE, and so they put it into hibernation. But situations at NASA changed, and it turns out people are awfully worried about rocks hitting Earth. And NEOWISE is very, very good about seeing those rocks. And so it was awoken in September 2013, rechristened NEOWISE, and it finally cooled off passively enough by December 2013, and it began the second post-cryo survey. And at the end of December 2014, that was the official end of its first year reactivation and the start of the second year. So this is a graphical representation of this because, as I said, it's going to matter downstream for understanding data releases. So this graphic you'll see again. So at first we had 4 bands. It was the all-sky survey. Then when the cryogen started to run out, we had 3 bands. Then the cryogen completely ran out, and we were left with 2 bands. And in between the start of the mission and that first hibernation, that all together, the data release that includes all of that data is called AllWise. But then it got reactivated, and the first big data release covered that first year of operations, which was essentially all of 2014. There'll be another release from the 2015 data and another release from the 2016 data. And remember that the sky gets covered completely every 6 months. And so this is just a representation of that. So how does WISE fit in? So if you're new at this, it might seem like we have an awful lot of space-based infrared observatories. Why do you need WISE? So there are 3 really big IR missions. There's Spitzer, Herschel, and WISE. And as I mentioned earlier, the telescopes are very different sizes. Spitzer is 85 centimeters, Herschel is 3.5 meters, and WISE is only 40 centimeters. Spitzer, when it had cryogen, could observe between 3.5 and 160 microns. Herschel, when it had cryogen, could observe between 50 and 700 microns. WISE, when it had cryogen, could observe between 3 and 20 microns. But the observatories are very, very different. Spitzer and Herschel point where we want them to point. WISE surveys the whole sky. And their orbits are very different. Spitzer is in an Earth-trailing solar orbit. Herschel was at a Lagrange point, at the L2 point, and WISE is in a sun-synchronous polar orbit. None of them have cryogen anymore, but they are still operating, just Spitzer and WISE are still operating for the shortest 2 channels, because some really clever engineering means the spacecraft can passively cool and continue to observe at the shortest 2 wavelengths. So 2 of the chronic trade-offs when you're planning whether you want an all-sky survey or a pointed observatory is 2 things: the spatial resolution of your data and the integration time, otherwise known as the survey depth. So if you're covering the whole sky, you usually do not have resources to stare just at one region. You have to get through the whole sky as fast as you can and still meet your goals. So survey depth corresponds to integration time. In other words, more integration time is deeper because you're able to see fainter things further away. So pointed observatories can point for hours or days or weeks or months even at the same object. All sky surveys usually have just a limited amount of time in which they have to do the whole sky, so they really got to book it. And if you're covering the whole sky, you really do need a wide field of view to do it efficiently. And typically then, your spatial resolution is not as good as the other pointed telescopes. And it's intimately tied to the size of the telescope, because wavelength is going to go as, resolution is going to go as the wavelength of the light divided by the diameter of the telescope. That's the formula there. So longer wavelengths means you have worse spatial resolution for a given telescope size, and for a given wavelength, smaller telescopes mean worse resolution. So one example would be the Palomar Observatory Sky Survey. It was taken in the 50s with the 48-inch Samuel Ocean telescope, but the really famous Palomar 5-meter is not a survey telescope. It is a pointed telescope to follow up discoveries from the All-Sky Survey, at least it was originally. Spitzer is 85 centimeters and Herschel is 3.5 meters, but WISE is only 40 centimeters, but WISE covers the whole sky. So here is the talons of the Eagle Nebula. It's the Hubble version of this region, is one of the most popular images downloaded from the Hubble website. They call it the Pillars of Creation. You can also think of it as the talons in the Eagle Nebula. So the original Hubble observation has this funny footprint because of the shape of their field of view, or the shape of their detector rather, and so they're focusing just on the talons. But Spitzer has relatively big field of view, and so it can cover this whole region pretty efficiently. So that little footprint there is the Hubble footprint, but you can see this whole region was observed by Spitzer. And in this 4-color Spitzer image, the 4.5, 8, 24, and 70 micron data are all represented. So the field of view is about half a degree on each side. And the longest wavelength shown in this image is 70 microns. And so the longest wavelength is depicted with the reddest color. So the red is the 70 microns and the blue is the 4.5. And the red here, how we interpret this image is the red is the hotter dust that was heated by a supernova 8,000 or 9,000 years ago. And so the blast wave from that is actually crumpling the towers just very, very, very slowly. So now I'm going to hit the button and we're going to go see what this region looked like with IRAS, which was the first infrared astronomy satellite. It was orbiting in 1983. I'm not making this up, folks. It is lined up. You can see the bright region up there is bright in both, and you can see the darker region down there is dark in both. So this was the previous survey mission, and now you sort of see why we needed to get both a pointed observatory like Spitzer, but also WISE. So here, red is the longest wavelength used in this image at 70 microns. Now, that is a Herschel image. Let's go back and forth, okay? Herschel, the shortest wavelength is 70. So for Herschel, 70 microns is blue, yellow is 160, and red is 250 microns. The Spitzer image has a lot more point sources, a lot more stars. The Herschel image has a lot more dust. Lots and lots of dust. So the dust that we see here is between 10 and 40 Kelvin. Now we're going to go to WISE. So it's blurrier. Definitely blurrier. Look how sharp that Spitzer image is and how blurry that WISE image is. But both the Spitzer and Herschel data stop. There's an end to those mosaics. But there's really no end to the WISE data. So you can investigate what the larger environment is. You can discover entirely new things like those dark lanes over here and that source, whatever that is. So since you don't have an end, since the survey, you can see the whole sky. The trade-off, though, is lower spatial resolution. So this is just, we'll have another video on the issues of spatial resolution, but I wanted to pull this out particularly. Here's the same chunk of sky seen in many different wavelengths. So across the top, we have the 4 WISE bands. So you can see WISE 1 and WISE 2 are comparably blob size. It's comparable resolution. 12 microns is a little bit larger because the telescope is staying the same through all 4 of the WISE bands, but the wavelength is increasing. So the resolution is getting worse. WISE is a little bit bigger, and 22 microns is enormous. The spatial resolution at 22 microns is not very high compared to the other bands. Now here's the same chunk of sky in J, H, and K from 2MASS, so near infrared. And there's the chunk of sky in the Palomar Observatory Sky Survey, so optical. You can see that JH and K and POS are similar spatial resolutions, and the source looks pretty much like a circular blob in WISE, and kind of circular in JH and K and POS, but if you have a really good calibrated eyeball, you might be able to see that it's not a circle, it's actually elliptical. When you go at it and look with Sloan, which is in the optical, higher spatial resolution than POS, you can definitely see that it is a nice little edge-on galaxy. So this is one example of why spatial resolution matters, and we'll talk a lot more about spatial resolution later. But the important thing to remember here is that when you're thinking about resolution, it really matters what wavelength you're talking about. The spatial resolution for WISE is a function of wavelength, and it's not the same as pixel size. So for the last big point for WISE, WISE is really good at finding rocks. Asteroids, because they're heated by the sun, they glow in the infrared, and they peak between 12 and 25 microns. So they're brightest between 12 and 25 microns. So WISE and its reactivated version NEOWISE is a rock hunting machine. It has observed hundreds of thousands of asteroids and comets and discovered hundreds of them. And these things are easy to find when they are close because they move as we take several consecutive exposures. So here is an image of an interesting astrophysical object. It's a long way away, but you can see these asteroid trails, right? That one is just this one. This one is that blown up. You can see that the asteroid is moving in between successive exposures. This one is going so fast it's a streak. There's another one up there. So this is why WISE was funded to be reactivated, because it's really, really good at finding these rocks. This is a movie that shows the discoveries of WISE. So here we have the orbits of the inner planets and Jupiter, and all of the black dots are new main belt asteroids that WISE discovered. The blue dots are the planets, the green dots are the previously known near-Earth objects, the red dots are the new near-Earth objects, the turquoise dots are the known comets, and the yellow squares are the new comets. So you can see as WISE is moving through its 6-month orbit, it's covering the whole sky, but the asteroids are moving too. And so the part of the population that WISE is seeing changes a little bit with time, and the edges sort of get smeared out as it's moving through the orbit. But you can see it really has revolutionized our inventory of the rocks that are out there. There is where it ran out of cryogen. You see it became less sensitive, and it was discovering fewer objects. That was the end of the first year, and it kept going. So this is a census. This is one of the big results from WISE. It's a census of all of the objects, the rocks that are out there. So the colored ones are the previously known asteroids, and the new total based on WISE observations is in green, and the old total that before we got the WISE data is in turquoise. So before we had WISE, we thought there were a lot more rocks out there than there turn out to be. That's good from a planetary protection perspective. It really has revolutionized our understanding of what we need to worry about. So the big asteroids, most of them we knew. WISE found some. This population, there's many fewer of them than we thought. This population discovered a lot of them, but still fewer than we thought. And the tiny ones, you know, about half as many as we thought. And the little tiny ones, we still don't know. That's why WISE is still looking. So NEOWISE is the name specifically given to the post-hibernation WISE, and NEOWISE, NEO meaning rebirth, but also near-Earth object. And so that's why it's really good at finding NEOs, and so that's what it's funded to do. It's worth pointing out that astrophysics, in other words, the study of things beyond our solar system, is not funding NEOWISE. The planetary people are funding NEOWISE. So there's no money available to sum up the images. The individual data frames taken by WISE go through the pipeline, but as soon as the asteroids are extracted, there's not enough money to go further, so they don't get added together. There's a tool that is available for those to add up those individual data frames, but if you want to sum up all of the available WISE data at a location, you have to do that yourself. So next time, we'll delve specifically into the WISE catalog, and just as a reminder, it is important to remember that overall WISE timeline, because it's going to influence which data delivery, which images, and which catalogs you choose to use.